Hi, my name is Daniel Kalny and I'm from the Czech Republic. In this presentation, I will show how GreenArray's chip GA144 can be used to implement a simple heart rate monitor. A heart rate monitor is a personal monitoring device that allows to measure one's heart rate in real time or record the heart rate for later study. Traditional heart rate monitors usually comprise two elements: a transmitter worn on a chest strap and a receiver. Those devices are based on detecting electrical signals produced by heart activity. More recent devices use optics to measure heart rate by detecting changes in blood flow. In this work, I have been interested in the first group of heart rate monitors based on electrocardiography principles. The electrocardiography is a process of recording the electrical activity of heart over a period of time using electrodes placed over the skin. In the simplest arrangement, only 3 electrodes are necessary, 2 being placed on arms and 1 on the left leg. The electrocardiograph then measures the voltage difference between left and right arms, the leg electrode working as a ground. ECG of a heart in normal sinus rhythm is composed of a small P wave, followed by a so-called QRS complex, followed by a T wave. The top of the QRS complex, the R wave, is a good point for detecting the heartbeat. By measuring time difference between consecutive R waves, we can easily calculate the current heart rate. In this demo application, I wanted to use even simpler electrode arrangement. In this arrangement, only 2 electrodes are attached to the chest and the electronics is referenced to a virtual ground. Though more susceptible to noise, this arrangement is much suitable for mobile applications. Cardiac activity produces very weak signals that are easily disturbed by different kinds of noise. In 1985, Penn and Tompkins published a paper showing how to digitally process ECG signal. The algorithm is mainly used for noise removal and to reliably detect R waves. As can be seen in this figure reproduced from the original paper, even heavily distorted ECG signal shown in the top trace can be used to detect R waves, as is shown in the bottom trace. This heart rate monitor demo project aimed at the following goals. First, to implement ECG signal acquisition using GreenArray's chip GA144 in the 2 electrode arrangement, then applying the Penn and Tompkins algorithm to extract R waves from the ECG signal on the fly and report the current heart rate, and finally to determine the energy consumed by the application. Let's have a look at the hardware used in this demo. The setup for this demo is simple. The voltage difference generated by my own heart activity is recorded between 2 ECG Holter type silver-silver chloride electrodes. This very weak voltage signal is then amplified in an analog module and processed digitally in the target chip of the GreenArray's eval board. Output from the GA144 is then sent to a PC running a CalForth application used for visualization. The analog module is based on the scheme published by YAP. The raw ECG signal is first conditioned with a low-pass filter with a cutoff frequency of 160 Hz. It is then amplified with an instrumental amplifier having gain of 21 dB. The differential signal then goes through a high-pass filter with a cutoff frequency of half Hz. It can be further amplified with this non-inverting amplifier. However, in this case the signal has been strong enough that I only use this op-amp as a buffer. With this buffer and voltage divider, we generate a virtual ground of 900 mV with respect to power supply ground. The whole module is powered with 1.8 volt supply, the same as GA144 chip. Now I will show a floor plan of this application. This demo is implemented in the target chip of GreenArray's eval board. It uses only 25 nodes, of which more than half is just wire nodes. This simple application consists of several parts. There is an external clock source. It is implemented as a 32 kHz crystal oscillator in node 517. When the oscillator is running and stable, it launches an analog signal sampler in node 617. The sampler uses ADC to digitize signal from ECG preamplifier. Digitized data are sent downstream to a signal processing block. This block implements the Penn-Tompkins algorithm. At the end of signal processing, node 612 detects the R wave and sends this information via its down and left ports. For the purpose of this demo, the ECG waveform is sent from node 616 via wire nodes through a buffer in 510. This buffer provides necessary time delay corresponding to Penn-Tompkins processing time so that the signal from R-wave detector is in sync with ECG waveform and can be combined in node 608. Here, fiducial markers are appended to data stream at points corresponding to R-wave peaks. This stream is then sent via async serial port in 708 to PC and displayed in a scrolling window of a ColorForth application. The signal from R-wave detector is also sent to beeper in 715, which generates a short beep whenever the R-wave is detected. Now we are going to see how the application is implemented in detail. The oscillator is described in GreenArray's app node 12. It uses a watch crystal and it provides a clock signal to analog node 617 via shared pin. The code from the app node is slightly modified to start 617 only when the clock is running and stable. Register A is pointing to up port shared with sampler node. When the crystal excitation phase ends and clock is not running, a zero flag is sent to 617. Otherwise, a non-zero flag is sent to it. Thus, 617 does not start sampling before clock is running correctly. The sampler is using analog nodes ADC. The ADC is basically a fast-running voltage-controlled oscillator which has linear response between 750 and 1300 mV. Setting virtual ground of the preamplifier to 900 mV ensures a sufficiently large interval of linear response at voltages above ground. This is desirable as a typical ECG waveform is non-symmetric, mostly positive signal. The node is sensitive to both rising and falling edges of the clock. The rate of clock ticks is too high for sampling and it's downsized to reasonable 256 samples per second. The code of the sampler node is following. The node starts suspended, waiting for a signal from clock node. When it comes, we enter word sample. Here, register A is first set to left port. It means that store instruction will suspend the node according to the state of wake-up direction bit in I/O register. In other words, it suspends the node until the next clock edge. Then we enter a loop skipping 255 clock edges. Notice that we use instruction store B to toggle the wake-up direction bit. Here we wait for the next clock edge before calling word ADC. Therefore, the sampling rate is 1 out of 256 clock edges, which is 256 Hz. Entering word ADC, this phrase turns ADC's voltage-controlled oscillator on by setting an appropriate bit in I/O register. Now we set register A to LData, which means that using store instruction does not suspend the node. Here we do the first reading of ADC counter. Then we wait for 500 micronext loops, which corresponds to approximately 1300 nanoseconds. And then we do another reading of the counter. We calculate the difference of the two readings, which corresponds to the voltage on analog input. Then the result is sent downstream. Notice that the stack is preset with values toggling wake-up direction bit and also keeping the VCO turned off except for the sampling interval. This is necessary to keep energy consumption low. Here we can see a recording of an actual analog signal digitized by the sampler node. When I stop the recording, you may notice little spikes that correspond to R waves buried in 50 Hz noise. Also, the signal is offset from the zero line. This has to be dealt with during the following signal processing. As shown in the introduction, the Penn-Tompkins algorithm is a robust method of detecting QRS complex in noisy ECG signal. It processes the raw signal in several steps. A bandpass filter reduces influence of 50 Hz interference, baseline wander, and T-wave interference. The desirable bandpass is approximately between 5 and 15 Hz. In this demo, only low-pass filter is implemented. High-pass filtering is provided by an RC high-pass filter in the signal preamplifier. After filtering, the signal is differentiated to provide QRS complex slope information. After differentiation, the signal is squared. This makes all data points positive and thus nonlinear amplification of the output of the derivative. The purpose of moving window integration is to obtain the slope of the R wave. The QRS complex corresponds to the rising edge of the integration waveform. A fiducial mark for the temporal location of the R wave can be determined from its rising edge. The Penn-Tompkins algorithm then uses several dynamic thresholds to detect the QRS complex which were not implemented in the demo application. The signal processing algorithm is implemented in these 5 nodes. The stream of sampled data is passed through a low-pass filter, a differentiator, a squaring function, a moving window integrator, and finally an R-wave detector. We start with the low-pass filter. It is implemented as a finite impulse response filter. Parameters for the filter were calculated using T-Filter, a web-based application. The filter was set to have a passband from 0 to 15 Hz and a stopband from 48 to 128 Hz. The stopband was set in such a way as to place a notch with -70 dB attenuation at 50 Hz. This is the code implementing 11 taps FIR filter. First, we fetch a new data, then we call word LPF. It uses word taps that is available in RAM of majority of GA144 nodes. This word is followed by a table with filter coefficients and temporary storage words, implementing a tapped delay line with summation of scaled taps. The coefficients are expressed as 17-bit signed fractions. Upon return from LPF, we discard the oldest raw value and send the filter output to left port for further processing and to up port to display ECG waveform in call-forth application. This recording shows how the signal from the low-pass filter looks like. Next step in data processing is numerical differentiation. We use a 5-point stencil approximation of the first derivative, which means that for each point xn, two preceding and two following points are also included in the calculation. Again, we use word tabs with 5 coefficients. The coefficients are taken from the original paper by Penn and Tompkins. The procedure is similar to low-pass filter. We read data points from left port, then calling the word d/dt, we calculate the first derivative approximation, and finally the resulting value is sent to right port. And this is the output of the differentiator. Next step is to square each data point. This is done by multiplying each data point by itself. Since data point values fit into 8-bit signed number, we can use a faster multiplication proposed by Chuck. First, we calculate an absolute value of the incoming data. Although squaring works with negative numbers as well, the multiplication procedure requires the multiplier to be unsigned. Next, we prepare the multiplicand by duplicating and left shifting the number by 8 bits, and we place the multiplier on top. Finally, we run the multiply step 8 times and send the result downstream. Squared signal looks like this. We can see a large amplitude of the signal where our wave is supposed to be. Another step in signal processing is moving window integration. We use a 32-point wide window. Its width has been set empirically to span full QRS complex. The algorithm is simple. For each point, we calculate a sum of the last 32 data points. The sum is stored on top of stack, which is preset to 0. And the most recent data points are stored in the array 32 words long, starting at address 0. A register is used as a pointer into that array. In the word sum, we first subtract the last data point in the array pointed to by register A from the sum. Then we read a new data point, store it in the array at the same place, advancing pointer by 1, and add the new data point to the sum. The pointer is rolled over if needed, and before sending the sum downstream, it is divided by 16 to simplify its visualization. Here's how the signal looks like after integration. It is a quasi-square wave signal with rising edge at the location of the original QRS complex, all other peaks being practically eliminated. The last step in signal processing is detection of R-wave position. The code compares relative change of amplitude of the signal. When it exceeds 7 units, an edge is detected. First we wait for a rising edge, which is detected with the word rise. When we detect this edge, we send a true flag to the left and down ports. Then we continue searching for a falling edge with word fall, and finding the falling edge, we send a false flag to the ports. When executing words rise and fall for each data point tested, we send a false flag downstream until the edge is detected. Thus, each data point tested generates a false flag, except for the only true flag sent when the rising edge is detected. The threshold value of 7 units has been set empirically. This is where the original Penn-Tompkins algorithm uses dynamic thresholds. Now we can append a fiducial marker to the ECG signal from the low-pass filter. We read a data point of the ECG signal and trim it in order not to overflow the scrolling window in the call-forth application. Words min and max are taken from Chuck's website. when we read a flag from R-wave detector and send both flag and data point to PC. The call-forth application then displays data points and fiducial markers, and it also calculates and displays the current heart rate, as can be seen in this visualization. The GPIO pin of node 715 is connected to a piezo buzzer. We continuously read flags from R-wave detector and call word beep on true flag. This word generates a short square wave signal driving the buzzer. And this is the resulting ECG signal with R waves marked also acoustically. Well, the application is running, measuring my heart rate, and the last question that remains to be answered is how much energy it consumes. Hence, I will be talking now about energy aspects of the application. And if we want to determine energy, we have to measure current. Current measurement is well described in GreenArray's application brief number 3, as well as the application note 12. Either on-board or external power source can be used, and it is recommended to use 6.5-digit ammeter, which has low shunt resistor value and a sufficient resolution. Alternatively, an external low-value shunt resistor can be used with low-resolution voltmeter. Though useful, this approach provides only average current. If we want to see current variation in time, another approach has to be used. Therefore, the following methodology has been tested. First, we remove a jumper between pins 2 and 3 on pinhead connector J14, which connects onboard supply power to VCC core. Then we place 2.2 ohm resistor between those pins, and a scope probe is attached to the pin number 2 as a high impedance input voltmeter. The idea here is to register voltage drop on the low value resistor in time and convert it with Ohm's law into current. The approach is simple, but when measuring a baseline signal with all target chip nodes suspended, I got this trace. After discussing the issue with Greg and doing some research, I found out that the oscillation comes from the onboard switching regulator, as can be demonstrated on this figure taken from LT3480 datasheet. The amplitude of the spikes is less than 15 mV, which is well within the specification. Though not a problem when supplying power to an application or measuring average current with an ammeter, it is nevertheless unsuitable for my method of current measurement with a scope. Therefore, the methodology has been modified. This time we connect pins 1 and 2 of J14 with a 2.2 ohm resistor and supply power to the core of the target chip from an external 3-volt lithium battery using a low dropout regulator. The scope probe is attached to the pin number 2. Now the baseline is flat and stable. However, when measuring current during heart rate monitor activity, we can observe inconsistencies such as voltage going above the baseline. This is obviously an artifact, as there should not be voltage higher than that provided by the voltage regulator. Again, discussing with Greg, he pointed out that the selected regulator is not really a good one during transitions, as can be seen on this figure from datasheet. The load transience response clearly explains why we measure voltage higher than that of the baseline. In order to solve the issue, a differential voltage measurement had to be used. Not having a differential scope probe, voltage on both pins 1 and 2 has been measured, and the recorded traces have been subtracted in a spreadsheet to get voltage drop on the shunt resistor only. Averaging data from 10 measurements leads to a reasonably noiseless trace suitable for further analysis. For current measurement, the application has been modified and all unrelated parts have been removed. There has been no ECG waveform recorded and no data sent to PC, and the beeper node has been converted to just trigger scope recording. Using this arrangement, such scope traces could be recorded. This is a current in time trace calculated from differential voltage obtained with the scope. The time scale has been shifted so that 0 lays at the moment when the current starts to rise above the baseline. The trigger point is then at the time of 4 microseconds, and we know that this is the moment when the node 715 is activated. We can analyze the trace from the beginning till the trigger point. This is the time interval when an analog signal is sampled, processed, and R wave is detected. The rest of the curve from the trigger point on must be related to recharging any capacitance that supply power during each current increase. This capacitance is due to filtering caps on VCC core power supply lines, as well as internal capacitances of the target chip and capacitances of the PCB. The trace of the active part has basically two stages. The first one with duration of 1.3 microseconds, which corresponds well to 500 micronext loops and can therefore be attributed to the sampler node. The second stage, lasting for 2.7 microseconds, can be further divided into three segments. One lasting 1.7 microsecond, which corresponds to execution of word taps 11 times and results from low-pass filter running in node 616. Then another of 0.8 microseconds corresponding to 5 times execution of word taps, which can be attributed to differentiator in node 615, and finally 0.2 microseconds, which is generated by a sequence of execution in node 614, 613 and 612. Now, when we can attribute individual nodes to the parts of the current curve, let's analyze the current magnitude for individual segments. In the first segment, current reaches 1.8 milliamps. Since only node 617 is active in this segment, we can identify two current sinks. One is corresponding to ADC's down counter running at the frequency given by the voltage controlled oscillator, and the other is due to micronext loop determining the sampling interval. The value for micronext loop is about 25% less than that reported in Green Array's databook. It cannot be explained solely by variation in manufacturing process, as this value should not deviate from the typical one by more than 15%. We have to assume that the current does not reach its peak value during 1.3 microseconds, and energy is partially supplied from capacitances even at the end of this segment. In the second segment, current reaches 4 milliamps, which is in a good agreement with Green Array's databook, reporting typical current for one node running at full speed between 3.25 and 4.25 milliamps. There are never two or more nodes running at the same time for a significant time duration. Thus the current and time analysis is consistent with expected values determined by the code being executed. Having analyzed current and time, let's focus now on energy and power. Charge passing through the target chip is equivalent to the area below the current versus time curve. It is therefore possible to determine the charge by integrating this curve numerically. We integrate the whole curve, including the part after the trigger point. This is necessary as it represents the charge supplied initially by capacitances. Doing so, we get charge of 16 nanocoulombs. To calculate the energy consumed, we multiply the charge by voltage. For the sake of simplicity, we assume the nominal voltage of 1.8 volt. The energy consumed is thus equal to 29 nanojoules. This energy is consumed for processing one analog sample. Multiplying the energy by sample frequency of 256 Hz, we get energy per second. This is the average power, which in this case is about 7.5 microwatts. Finally, dividing the average power by voltage, we get the average current of about 4 microamps. Why all those simple calculations? Because a lot has been said about GA144 being a low energy chip, but rarely it's shown what it means in practice. For instance, how long time could we run the heart rate monitor from a battery? Let's see. A single CR2032 lithium battery has capacity of 235 mAh. According to GA144 databook, the chip draws 7 microamps when fully suspended. The application draws about 4 microamps. So we need about 11 microamps on average. At this rate, a single 3-volt lithium battery could supply power to the heart rate monitor for almost 2.5 years. With this lifetime, even Forrest Gump would not have exhausted a single battery during his legendary cross-country run. As a conclusion of the presentation, let me express some thoughts on the topic. There are several areas where the application could be extended in order to work as a real product. First, the ECG electrodes could be replaced with capacitive ones. This eliminates the need to have a good electric contact of the electrode with the body and makes the use of the monitor more agreeable. The information about heart rate could be transmitted wirelessly, for instance with the AND protocol or low energy Bluetooth. There are many ready-to-use modules for such wireless communication. A smartphone application to display the heart rate and to provide other useful functions would be needed as well. Although it has been shown that a single coin battery can supply power for a relatively long time, it would be definitely interesting to incorporate an energy harvester into the heart rate monitor. It could harvest energy, for example, from vibrations or heat generated by the body. Though not part of my current plans, I still may test these extensions in the future. I'd like to express my acknowledgement to GreenErace for providing me with the eval board. Also, I would like to thank Craig Bailey for invaluable discussions and Jack Moore for sharing his Harry Forth code. Thank you for listening.